So now that we have a basic understanding of entropy, which you probably were introduced to in your General Chemistry 1 class, we can sort of summarize the first and second laws of thermodynamics. And the first one's the most intuitive one, which you think about and operate within without even really considering it. And that's just the conservation of energy. You can't make or create energy, and it gets conserved in every process. So we can transfer energy from one form to another, potential or kinetic or chemical, whatever it may be, but it is always conserved, meaning the equations always add up to the same thing that you started with. It doesn't mean it can't be subdivided and lost in different forms, which is really what the second law is speaking to. So the second law can be interpreted in lots of different ways, because of course it's a mathematical thing. But in words, one way to think about it in terms of entropy is that the entropy of the universe is always increasing. Always has to be true. So the universe is always striving towards more randomness, greater disorder in the system. And a consequence of that, or another way of thinking about the second law, is that not all energy can be converted, even within the bounds of conservation of energy, to work. And that's because some amount of that energy is always lost to inefficiency because of the increasing entropy of the universe. So you're always sort of donating some energy to the universe to satisfy this condition, which means you can't take 100% of energy and convert it to another form. And that is really the crux of the sort of perpetual motion machine. And that leads us to this third law. And so the third law is going to help us understand some of these concepts of spontaneity and also tabulation of entropy change. So we know the universe always needs the entropy to be increasing. The third law states, sort of in its simplest form, back when Nernst formulated it originally, that if you sort of could hypothetically have a pure substance, right? So a pure elemental substance that was arranged in its perfect crystalline state, so the most highly ordered state of that system and the simplest version of that system. And you could simplify it even more by making sure that that crystal of that pure element, no impurities at all, was at absolute zero. That's T equals 0, which is, all of this is impossible to achieve experimentally, but this is a fictitious state, a hypothetical state. If those conditions were satisfied, then that system would have an entropy of 0. Another way of thinking about that is that anything in the natural world has an entropy greater than 0 because it's either not perfectly ordered, it's above a temperature of 0, or it's a compound made up of more than one element. And so really this may feel obvious, but it's sort of an axiom that states that everything has some disorder if you relate it to the sort of perfect example of purely ordered system. So another way to think about entropy is through this expression, which is a really powerful expression where S is entropy, K is some constant, which is called Boltzmann's constant. It's a really important constant that's related to, it's essentially the gas constant divided by Avogadro's number. So it's really just the gas constant normalized to individual molecule. Natural log W. And W is this sort of cryptic thing here, which is really the number of different ways that this individual state could be configured or arranged. And of course, if you want something to be more disordered, having higher entropy, then you want more available configurations for that state. And so that makes sense that entropy is directly then proportional to the number of states. If you go on to take a physical chemistry course or a specific flavor of physical chemistry called statistical mechanics, then you do a lot of actual statistics because these are probabilistic things where you can say, well, what are the possible available states, or what we call microstates, that a compound or a series of compounds can exist within? And the more that could exist, the higher the entropy of that. And that should make some sense too when we compare this to a pure crystal, because when you have a pure crystal and you have a molecule or an atom that's locked permanently and fixed in space and cannot move, and it's at T equals 0, so it can't vibrate or translate or do anything, then the number of possible configurations of that state are quite small, or maybe constrained to 1, which means that that system goes to 0. And that really sort of justifies that third law of thermodynamics, in that extreme case where you have a crystal and no impurities, and that thing can only exist in that one possible configuration, the natural log of 1 is 0, and the entropy of the system is 0. But we know in reality there's always going to be some wiggle room here under any truly natural condition. So let's revisit the second law of thermo again and think about another sort of flavor of interpretation. We've already sort of established that the second law states that a spontaneous process means that the total entropy of the system is increasing, but we haven't been explicit in differentiating where we're accounting for that entropy. And so it's important that in any thermodynamic process we are clear about what the system is and what the surroundings are. And so for the entropy of the universe to be increasing, which is what the second law states a spontaneous process should do, we account for that as the total entropy change, which includes both the system and the surroundings. So the system is the reaction itself. It's the thing that's undergoing the change, but that system has to be in the universe, and so somehow there's an exchange of energy in the form of entropy between that particular system change and the place that it's existing within. And so it's the overall change that ultimately dictates the spontaneity, not simply the change of the reaction or the system in this case. So the system is really the sort of standard molar entropy change that we've talked about and will continue to talk about, the thing that we can account for simply by looking at the molar entropy of the products minus the molar entropy of the reactants, very similar to what we have done with enthalpy. But how do we think about the entropic change to the rest of the universe, the surroundings that the system was with? But I won't derive this expression because that's a long road and best reserved for a more advanced course in thermodynamics or statistical mechanics. But we can look at this form of the equation, and it's a really simple one. And so it's the negative change in enthalpy over the temperature of the particular system that the surroundings are within. But what does this mean to us? Remember, if we want this delta S to be positive, if we're thinking about a spontaneous reaction, so that means the more positive and large either of these values are, the more likely this system will be spontaneous. So if we're just thinking about the change in the surroundings, what does this mean for us? Well, we know that when delta H is negative, that means heat is liberated from the system, right? So for exothermic systems, then we have a negative delta H. And so if we're inputting a negative delta H into this expression, then that turns this top term positive, right? Which means that there's an overall positive change of entropy to the surroundings. So what that tells us is that when there's heat released from the system, then the surroundings have an increase in the overall entropy. So heat released to the universe increases the entropy of the universe. That's the general takeaway from this term. Then generally the larger that heat term, then the more intense that contribution is to the overall total entropy change of the system, or the total. So knowing what we know about entropy and the fact that spontaneous reactions are actually governed by whether or not the spontaneous of the the entropy of the universe is increasing. That's the total delta S, which is really a contribution of the system, which is the reaction, and the surroundings. That's the stuff that the reaction was within. Let's look at this example, which is the rusting reaction. This is just iron metal plus oxygen gas makes Fe2O3. That's rust. And let's see if we can figure out what the sign, positive or negative, of the total entropy change is for the system, and then use that to evaluate whether the system is spontaneous at 25 C. So in order to figure out the total entropy change, then we just need to think about what the difference is in the the entropy change to the surroundings and the entropy change to the system. So here we're talking about the system first. So let's find the delta S of the system, which is really just comes from the standard practice that we know how to do, which is look at a table of molar entropies of the products and reactants, and then just sum up the products, subtract the sum of the reactants, and then you get an overall delta S for the reaction itself. It has nothing to do with the surroundings. And so these all just come from a table, which you can look up online or in a book. These are all under standard temperature pressure conditions. What we get is a value of minus 549.5 joule per Kelvin based on these table values. And that maybe makes some intuitive sense. This is a negative entropy change for this system, which is unfavorable, right? That's not helping us in our delta S total. But that makes some sense because we're talking about two different things here, a chunk of metal and some gas, and we are combining them into one solid substance. And so in terms of degrees of freedom of motion or movement, this is far more constrained, this product, because you're taking a gas which has tons of mobility, lots of randomness, and you're locking that down into the form of this solid. So that makes sense that this is a negative change in the entropy just of the system, this reaction. Okay, next step on our way to get the overall entropy change, the total here, we need to get the delta S of the surroundings. And we just talked about the expression for that is the negative change in enthalpy divided by the temperature. So that means we need this term. We need the delta H for this overall reaction. Again, we'd go to a table, we'd find what the individual enthalpy changes are, or the enthalpy of formation for each of these things, and we would take products minus reactants. So I'll skip that part because that's something that you know how to do well from back in Chem 107. So we'll just tabulate that. We get an enthalpy change under STP of minus 1648.4 kilojoules, remember, and then the delta S surroundings. Remember, delta S entropy is typically in units joules per temperature unit, or Kelvin often. So that means if I plug this in, I'm going to plug this in as negative 1648.4 times 10 to the third joules. So I'm converting this kilojoule to joules, dividing by units Kelvin. We're being asked what this is at 25 C, so this is 298.15 Kelvin. That gives me a value of 5529 joules per Kelvin. That's a positive. Okay, so last step then is to figure out what the delta S total, what's the overall entropy change of the universe when this reaction occurs. That's just going to be the sum of the two surrounding and system terms that we've already computed. So that becomes this big, large positive number, which was the contribution to the surroundings, which makes sense because this was a lot of heat that was liberated. And then we're going to add the negative of this. So that's actually bad, right? That's not helping us because that's a decrease in the entropy of this system, but it's relatively small. It's about 1/10 of what the overall change of the surroundings is. So in the end, we have a very large positive change in the overall total of this system, which based on the second law of thermodynamics says that if this is a positive value, if the sum of these two contributions to entropy, if that's overall positive, then this is a spontaneous reaction. And so we would make the determination that this is in fact spontaneous. One last thing we can do is actually check this assertion that this is a spontaneous reaction against the free energy change, the delta G of the system, because delta G is also a measure of whether or not the system be spontaneous, as we'll talk about. So if this is negative, then we can also assert this is a spontaneous reaction, and delta G is equal to delta H minus T delta X S. But it's important to know where these numbers are coming from. So when we're thinking about delta G of reaction, we're talking about the system. And that's true also for the change in entropy. So the change in entropy for the reaction is the change of the system, because that is the system itself. So this is not the total change. We're not accounting for the surroundings. We're just thinking about the system. So the utility in delta G is we can think just about the system, and it serves as a proxy to tell us whether or not it's spontaneous. But if we only have values of the entropy change and we have no information about delta G, then we can still make an assertion about spontaneity simply by the overall entropy change of the system total. So plugging in numbers should look something like this. So that original delta H reaction is what we had already tabulated. That's that minus 1648.4 kilojoules minus the temperature here, 298.15 K, times the delta S for the system, which we computed up here. But note that's in joules per Kelvin, and to make that work with kilojoules, you would multiply that by 10 to the minus 3, so that's why if the minus 549 goes to minus 0.549 joules per Kelvin, the Kelvin goes away. That allows us to compute the value delta G of minus 1484 kilojoules. So negative delta G's are spontaneous, and so our assertions are consistent with one another. So large positive delta S total means spontaneous. Large negative delta G for the system or the reaction is negative, that's spontaneous.